Hello, welcome to Super Easy Physics and Mathematics. I'm Orisheje Matthew. If you want to fail the next IGCSE Physics examination, you don't need to watch this video, just skip it over. But if you want to crack the next IGCSE Physics examination, then you need to take your pen, your paper, so that we can walk through this video attentively. And at the end, you'll be glad you did. So this is the modern answer to IGCSE Physics Paper 1 Extended. And we are going to use variant 1 of the May-June 2024 model. All I want to do is just to give you ideas and then review all the concepts in all the different topics that are captured in this examination series. So let's jump in. You are expected to answer all the questions, and this particular examination, the total mark is 80. And the major constant that you need to use throughout this exam, which is acceleration of free fall, is 9.8 meter per second square. So this is the value you are using, not 10. Take note. All right, so let's look at question 1. Question 1 is all about a ball falling through an oil in a container. So in figure 1.1. So a small ball is held at rest at the surface of oil at time t0. The ball is released and begins to fall vertically through the oil. Now, as the ball begins to fall through the oil, it accelerates. Very good. So what is the definition of acceleration? Acceleration is the increase in velocity per unit time. The formula is A equals to delta V over delta T. And the unit of acceleration is meter per second square. So that is a unit. All right. Question 1b. The mass of the oil is 0.0075 kilogram. Calculate the resultant force acting on the ball when it's accelerating downward at 2.8 meter per second square. So we want to calculate the force acting on the ball. And to do that, all you need to do, remember, the resultant force is the product of the mass of the ball and the acceleration of the ball through the oil. So we're given the acceleration here, and then we are given the mass here. So substitute, and that gives you the force of 0.021 Newton. All right, 1C. As the ball falls, its speed is recorded. Figure 1.2, this graph is showing the speed time graph for the falling ball. Describe what happened to the acceleration between time 0 and time 0.04. That is the entire of this graph. So this graph is depicting the time taken for the ball to fall from the top when it was dropping up to this point, this time here. So that is the duration that this graph is showing. Describe what happened to the graph. So if you look at this curve, it will show you what is happening to the ball, the acceleration of the ball. So at the beginning, the ball accelerates with a constant speed. This acceleration increased from 0 to 0.045 meter per second at this point in 0.04 seconds. That is the entire overview. Then let's look at the session. Then the acceleration decreases to 0 at this point because the graph, the VT graph, becomes parallel from this point. It's now parallel with the time axis. So it's parallel with this time axis. So at this point, the acceleration is equal to 0. Once VT graph is parallel to the time axis, the acceleration is 0. Then the acceleration remains constant from 0 to 0.04, from 0 to 0.025. Then the resultant force acting on the ball as it's falling through the oil keep on decreasing until it became 0 at when the ball attained the terminal velocity as it's falling through the oil container. Now, by drawing a tangent on figure 1.2, determine the value of the acceleration of the ball at time 0. At this time here. So that is from at this point, draw a tangent. Because the acceleration is a variable acceleration, so once you have a variable acceleration, a VT graph that is a curve, in order to find the acceleration, what you need to do, you draw a tangent to the curve. So if you do that, you draw a tangent that just touch the curve at that point given to you at that instant. So if you do that, then next, you can now find the vertical increase and then the horizontal run. So using your normal method of finding gradient, so can I find the gradient, which is delta V over delta T. So that gives you the gradient of 1.18 meter per second. And then the value that acceptable, that is if it lies between 0.1 and 1.8. So the acceptable value lies between 1.2 to 1.8. So any value you get there is correct. Okay. Question 2. Figure 2.1 show the identical pulleys, trolleys. That is what you have P and Q. Held at rest on a frictionless surface. So this is a frictionless surface. And then a load is placed on P to increase the mass. There is a compressed spring in between. That is a black layer here. Then the trolley is released as the spring expands. It pushes the trolley apart. Trolley Q moves to the right with the speed of 0. So this moves with the initial speed of 0.36 meter per second. Okay, then the mass of each trolley is 1.2 kg. The mass of the load on the trolley P is 1.5 kg. The spring has a negligible mass. Okay, so we have those information. Next, calculate the speed at which trolley P move to the left. So this trolley P will move to the left, and then trolley Q speed off to the right. So we are going to use the principle of conservation of momentum, that the total momentum, so the momentum of P, which is the mass of P, so you have to add the total mass, the load placed on it, and then the original mass will give you 2.7 is equal to the momentum of Q. So if you use that, substituting the value, we are looking for the velocity of P to the left. So you make Vp sort of formula, and that gives the velocity of 0.16 meter per second. Next, what is the kinetic energy of trolley Q when it moves at the speed of 0.36 meter per second? So so we are interested in the kinetic energy of this trolley. So the kinetic energy, Ke, is equal to the mass of the trolley multiplied by the square of the velocity of the trolley divided by 2, and that gives 0.078 joules. Now, state the energy transfer that takes place as the spring expands. So this spring, this spring that is in between the two of them. So as the spring expands, that is, the length grow longer. What is the energy? The energy stored in the spring is elastic energy, potential energy, and then as it expands, it pushes the two trolley away and the trolley start moving. So from elastic potential energy to kinetic energy. So that is the energy transfer that takes place in the spring. Question 3 shows a small block of ice, that is this, floating on a beaker of warm water. So the temperature of the water is hot, so it will cause the ice to melt. State one way in which the motion of the particle in ice differ from the motion of the particle in the water. So what we are looking at, the molecular structure. So you know that ice is solid, so the particles are closely packed and they vibrate in one location, a fixed location, while in the warm water the particles are slightly far apart and they can move over each other. So the particle in ice vibrate in one fixed location, then the particle in water move through the liquid. Energy is transferred from the water to the block of ice. State the name of the thermal process that transfer energy from the water to the ice. That is conduction, because both the ice and the water are in contact. Then initially there is 0.34 kilogram of water in the beaker. The specific capacity of water is 4,200 joules per kilogram per degree Celsius. Calculate the energy transfer from this water as its temperature decreases from 28 degree to 10 degree. Now, the temperature of the warm water is decreasing because it's transferring energy to melt the ice. And now, so look at this time here, specific heat capacity. So that is the quantity of heat required to raise the temperature of a unit mass of water by 1 degree Celsius. So that is what is called the specific capacity, which is 4,200 joules. That is the quantity of heat needed. So how do you calculate that? So energy transfer is equal to the mass of water multiplied by specific capacity multiplied by the temperature drop. So we can substitute that, and then you get the amount of energy. Then you express this answer to two significant figures. So that gives us 26,000 joule. The temperature of the water near the ice decreases first. Explain how convection causes the temperature of all the particles in the beaker to decrease. That is easy. So what we are looking at is the convection. That is a process that takes place. So you have in the beaker, you have inside the beaker, we have the water particle that is here. Then you have the particle at the top close to, so the density of the ice, of the water next to the ice increases. How does the density increase? So let me explain. So you have ice here. So there are some particle, let's use this one. So this is a particle close to this ice. Now because the temperature here is, there's a decrease in temperature because the ice is cooling this particle, so the speed of this particle is going to reduce. And as the speed reduces, it leads to what? A shrinking, that is a decrease. When the speed reduces, then this water is contracting. Like if you look at the anomalous expansion, okay, so what happened? You see this. So from 0, one, there is a cooling process. So there is the speed, first of all. Let's just go. So the water begin to sink because the density increases, so it's going to be heavier. And so because it's heavier, it's sinking to the bottom. So the heavier water goes down. And then the warm water at the bottom, it has is light because the density is lower. So the warm water rises up. So it's going to cause a convection. And then the warm water rises to replace the cold water, creating a convection in the container. Now, state what happens to the internal energy of the water as the temperature of the water decreases. Okay? Now, so we're going to look at the change in terms of energy of the particle. So what happened? Now, as the temperature of the water drops, the internal energy of the water decreases because the average kinetic energy of the particle decreases because there's a drop in temperature. So the ice cooled the water, and then it's going to lead to drop in temperature, and then the drop in temperature is an indication that the average kinetic energy of the water has reduced. So, and you know, kinetic energy is related to the internal energy because kinetic energy is equal to half mv squared. So once there is a decrease in velocity, then the kinetic energy also decreases. Question 4. The lens is a magnifying glass. So figure 4.1 show the lens of a magnifying glass and its two focal points, F1 and F2, and its principal axis, that is a line that passes through the middle of the. Now state what is meant by focal point. Now if you have a ray of light parallel to the principal axis, once they strike the lens, they are refracted and then they pass through the focus. So that is a point where a point on the principal axis where ray of light parallel to the principal axis incident on the converging lens converges after passing through the lens. Now, a student using magnifying glass sees a magnified image of the object in figure 4.1. Now, mark point S on the principal axis for a possible position of the object and where the eye of the student will be positioned. Is it on the left or on the right? So for a converging lens to produce a magnifying image, then the object must be placed at a position less than the focal length. So you place it at that point there. Any place between the focal point and the center of the lens, either here or here, you get the correct answer. Then if you put it here, then the student has to be on the opposite side. So the eye will be here to look at the glass. So both the object and the image will be on the same side. So let's just review the ray diagram. So we take that, then you put the object there. A ray of light parallel to the principal axis is refracted through the foci. So then a ray of light from the top of the image passing through the center of the lens is unrefracted. On the right hand side, it's diverging. So the only way the ray can meet is towards the left. So we have to extrapolate the red line and the blue line. So extrapolating where the intersection indicate the position where the image is formed. So the image is formed there. So this is the magnified image. It is visual because it's on the same side as the object and it is upright. So this is the three major properties of the image. So let's go to the next question. Now underline two words in the list that describe the image produced. It is not inverted, it is not real, it is upright and visual. So this one means that they are on the same, the image is on the same side as the object. Now the refractive index of the glass used to make the lens is 1.5. The speed of light is 3 times 10 raised to 8 meters per second. That is 300 million meters per second. Calculate the speed of light in the glass. So what you do is, let me just show you this. So what we are showing here is you have air, then you have glass, the lower part. Then if I draw here a normal, then the ray of light coming from the air strike this, then on entering into the glass, it bends towards the normal. So because the speed reduces, the wavelength reduces, and then the frequency remains constant. So all right, so let's do that. So we have the refractive index is equal to the speed in air over speed in glass. So with that, make speed in glass subject of formula, and that gives the value of 200 million meters per second. I don't want to give further explanation so that the video will not be too lengthy. So but I'm going to make another video to explain all this concept. Okay. State what happened to the wavelength of light as it passes into the lens. I've already said that wavelength reduces. Okay. Now, what is wavelength? Wavelength is the distance traveled by a wave in one complete oscillation. So that is what is called wavelength. So if you have the understanding of that, so let's see if this is a wave. So so in this distance, so how far the wave travel, this is the wavelength in one complete circle. Okay, now the wavelength is longer in air. Then as soon as you enter the glass, then it becomes shorter, it reduces. Okay, so wavelength reduces. Converging lenses are used in glasses spectacle to correct one problem with vision. State the name of the problem, okay, and explain how a converging lens is used to correct the problem. You may draw a diagram. What is the name of the problem? It's long-sightedness. Okay, Now, if okay, let me just draw this diagram for you here. So you have this is what happened. You have the human eye. Okay. Then the optic nerve. Okay. So a ray of light from distant object coming strike the lens of the eye, then the image is formed behind the retina. The major problem here biologically is say the eyeball is too short. Okay, so or the focal length of the natural lens in the eye is too long, so he focus image of objects, of close objects behind the retina. So to correct this, if you wear a glass here, so wear a conversion light, so this glass is going to make the image, all right, to come to the back and then is focused on the retina to form a sharp image. So that is what happened to that correction. Now quickly, let me just explain something, a mnemonic that help you to remember how to correct long-sightedness, hypermetropia, and short-sightedness. Now convex lens, if you look at it, the middle is long, so this one will correct long-sightedness. And then converging lens, look at the middle here, it is short, so this one corrects short-sightedness. So this will control myopia, and then use this to, when you wear a convex lens, it will control long-sightedness or hypermetropia. Now, question 5. Describe how a longitudinal wave differs from a transverse wave. Well, it's very easy. Actually, there's a video I'm working on that will explain exploring longitudinal wave. So just watch out away, upload it, and then have a better view of this. But let's just answer this one based because of the question. So we have 2 marks. You are expected to state 2 valid points here. Now, longitudinal oscillation in wave is parallel to the propagation direction of that the wave travel. So if the wave is traveling to the right, then the particle of the medium will oscillate left to right. If the wave is traveling from the bottom to the top, then the particle will oscillate up and down. Okay, so the direction is always parallel to the direction of propagation of wave. But for transverse wave, the direction is perpendicular. So you have, this is wave direction, then the particle of the medium will vibrate perpendicularly. Okay. Then longitudinal wave have compression and rarefaction, while transverse wave has crest and trough. Now this is compression, position J, where the particles are close, then alternate with where the particles are far apart, then the particles are close. So you have rarefaction, compression, rarefaction, compression, rarefaction, then compression. Okay, now quickly, okay, then let's explain how to get the wavelength. You were told the wavelength of this P seismic wave. The wavelength is 12 kilometers, and that is compression to compression. Then JK is compression to then rarefaction. So compression to rarefaction is half wavelength. So this is 1 wavelength plus. So this from C CRC